The integral is two main things. It is the area underneath the curve and the antiderivative. Well, this is climb time, and in this video, we'll look at why the integral is the area underneath the curve. So here we have an example of the notation of the integral. It's the integral, this is an integral of f of x dx from a to b, and that equals the area underneath the curve. When we say that, we mean it's the area between the function and the x-axis. And the area can be positive if it's above the x-axis or negative if it's below the x-axis. So this little area right in here would be the area we're referring to in this case. It's the area between the function and the x-axis. So what we have here are three pieces. This piece right here, this is a little small change in x. It's a very, very small change in x. We could even call it infinitely small. And what we have here is a y value. And what we have here is an infinite sum. So we have three pieces, a y, an infinitely small change in x, and an infinite sum. So those are our three pieces right there. So if we look at a little rectangle, little tiny rectangle, and let's say this little tiny rectangle has a height of y, and it has a width of dx. If we took y times dx, what we would have is a little tiny piece of area. And so there's many rectangles in here. In fact, we could say there's an infinite number of little rectangles in there. And each one is side by side. There are no gaps and no overlaps. And so a little tiny piece of area, we'd call that dA. dA is a little tiny piece of area. That's going to be the area of one rectangle. So in this case, it's height times width. So it's y times dx. So a little tiny piece of area. In fact, it's infinitely small. So this is a small piece of area. And it's so small, we would call it infinitely small. So as small as you can possibly imagine, a small piece of area is going to be a standard height. It is not a particularly small height. It could be any height. It could be small height, but it could be a really large height. Any height whatsoever times a little tiny small width. And that gives you a small piece of area. So imagine this rectangle, this little tiny rectangle is in here somewhere. Okay, and it has a little tiny width. A little tiny width is dx, and it has a height that reaches up to the function. That's why the height is y, because the height of that rectangle goes up and it's bounded by the function at the top. Because it's bounded by the function at the top, that is why its height is y. So a little tiny small piece of area is called dA. So if we want to add up all of the areas, if we want to take the sum of all the areas, so that's where this comes in. This is the sum of all the little tiny pieces of areas. So if you add up all the little tiny pieces of area, you're going to have the total area. So the integral of dA is the same thing as the, whoops, I do that sometimes. I accidentally hit the light button. The integral of dA is the same thing as the integral of y dx. And y is the same thing as the f of x. So this is the integral of f of x dx. And so because it's an infinite sum of little tiny pieces of area, you end up with the overall area. So maybe using a different color this time. This is going to be what we'd call, it's not the actual area, we'd call it the change in area. The change in area. So this right here is positive area. If we had negative area, the overall change in area could be zero, because you can have positive and you can have negative. But that's why the integral is a little tiny piece. The integral is the area underneath the curve, because the f of x represents the y value, the height of a rectangle. The dx represents the width of a rectangle. And height times width gives us area. And so this is one little tiny rectangle, the area of one little tiny rectangle. And this s, this integral, represents the sum of all the little tiny pieces of area. So if we add up all the little tiny pieces of area between A and B, we end up getting the total area. And so that's why the integral represents, yes, the antiderivative, but also an infinite sum of little tiny rectangles. And because it's an infinite sum of little tiny rectangles, it comes out to be the area underneath the curve. All right, so that's one piece. So it's important that you understand that these represent the two parts of a rectangle. When multiplied together, they give you the area of a rectangle. It's also important to recognize that when you see a D in front of something, that it means it's infinitely small. It's really small. So dA would be an infinitely small piece of area. And then it's also important to recognize that when you see this integral sign, um, the integral basically means it's an infinite sum. So if we take the infinite sum of infinitely small pieces of area, you end up getting the total area. Okay, so hopefully that makes some sense. Now what we're going to look at is the velocity curve. So let's take a look at the velocity curve. Right now, let's look at application of this. So let's see what it looks like specifically if the function is velocity. So let's say we have a graph and the y-axis is going to be v and the x-axis is going to be time. And a good velocity curve, well, it could look like a lot of things, but one example could be something like this, a little squiggly there, but something like this. So when you are at a stoplight, let's say with your car, and you hit the accelerator, your car starts to move. So you go from zero velocity to a non-zero velocity. And so your velocity is getting bigger and bigger and bigger. And your velocity could be negative if at some point you stop and you back up again. So your velocity could go negative. But in this case, the example of accelerating from the stoplight, that your car will keep speeding up. And at some point, you'll probably hit a terminal velocity. I don't know if terminal is the right word, but you'll flatten out, which basically means your velocity is not increasing anymore. So your velocity is getting bigger, bigger, and bigger, and eventually your velocity is, you're kind of cruising, you're at cruising speed. It's probably the speed limit, hopefully. And so that's what a velocity curve could easily look like after being stopped at a red light. So if we wanted to find the area underneath the velocity curve, what does that mean? So let's say from A to B, and I want to find the area underneath here. What would that area represent? We have a velocity curve. We have a velocity curve. What does the area underneath the velocity curve represent when you have velocity on the y-axis and time on the x-axis? All right, well, what's helpful, and actually let's write that down. What is the integral of v of t dt? What does that give us from A to B? And by the way, A and B are times, so what does that come out to be? That's what we want to know. All right, well, it's helpful to remember from earlier that velocity and instantaneous velocity is defined as ds over dt. It's the derivative of the position function. And another way to look at this is that it is the slope of the position function. So it's rise over run, but the rise is infinitely small. The run is infinitely small. And so if the rise and run are infinitely small, it hones in on a tangent line. So it becomes the slope of the tangent line of the position function. And so it becomes your velocity at an instant. That's what we would call the instantaneous velocity. But you can see the definition of velocity right there. We know that average velocity is equal to change in position over change in time. That's how velocity is defined. It's change in position over change in time. That's your average velocity. So to find an instantaneous velocity, which a curve represents, each one of these points represents an instantaneous velocity. So yeah, your instantaneous velocity is 0 there. Your instantaneous velocity is a little bit more there, a little bit more there, a little bit more there. Your instantaneous velocity keeps growing, and eventually it reaches a number where maybe it's 45 miles per hour. And so it's going to stay at 45 miles per hour because that's the speed limit. So your instantaneous velocity is defined as the derivative of the position function, but it's also defined as change in position or change in time. And more specifically, it's an infinitely small change in position, infinitely small change in time. The average velocity is a much bigger change in position or change in time, but instantaneous velocity is ds over dt. Okay, with that in mind, we can multiply both sides by dt. And so on one side, we get, I'm going to go ahead and switch the left and the right. So on the left, I'm going to have ds. And on the right, I'm going to have v of t dt. And all I did was multiply both sides by dt, and then I switched the left and right side. And what we see here is we have right here, this ds represents a really tiny small piece of something. And that little tiny small piece is a little tiny small piece of position because ds represents a change in position. So it's a little tiny small piece of change in position. So I'm going to say small change in s. It's a very small change in s. So you could call it an infinitely small change in s. So when I add the integral sign, so I say integral of ds, what I'm going to have now is an infinite sum of those small changes in position. So an infinite sum of the small changes in position, and that's going to be the same thing as the integral of v of t dt. And this is from 2 times. So this, instead of saying a and b, I'm going to say t1 and t2, because that's what's on the x-axis is times. And what that's going to give us overall is the sum of all the little tiny changes in position is going to give us the overall change in position. So we call that change in s. So if you want the overall change in position, you can integrate the velocity curve with respect to time. But that means 2 things. One, it means you can find the antiderivative, which we're not going to do in this video. But the second thing we can do is we can find the area underneath the velocity curve because it's an infinite sum of infinitely small changes in position. So if you take an infinite sum of infinitely small changes in position, you get the overall change in position right there. So this is going to be 2 things. It's going to be the area underneath the velocity curve. That's one thing it's going to be. But the second thing it's going to be is your change in position. So area, and that's going to equal your change in position. All right, so now we have to be careful here. So while that's true, oh, it looks like it went off the screen just a little bit here. Maybe I can bend that down a smidge. All right, so the area is your change in position. All right, so while that is true, we have to be careful of something here. A change in position is not the distance traveled. In this case, it would be. The area underneath the curve, which is a change in position, would also represent the distance traveled from A to B. But it's not always that. So I need to show you an example of what I'm talking about. Let's say that we have, and I'll just do it right here. Let's say we have a curve that looks something like this. It goes up. Actually, no curves like this. It's called sine and cosine. So sine and cosine looks something like that. And what would happen here, if you look between this A and this B, so if you look between here and here, if this is A and this is B, then this area would be negative, and this area up here would be positive. And assuming it's like a sine or a cosine, assuming you have symmetry, my drawing is not the best, but assuming you have symmetry, and this is a velocity curve, so this is V, this is T, that means the integral of V of T, and this is the velocity function dt, is going to equal 0. And the reason why it's going to equal 0 is because all the positive area is canceled out with all the negative area. And so that means your change of position is 0. But that doesn't mean you didn't travel anywhere. It just means you ended up where you started. A good example of this is going in a circle. If you go in a circle, you will end where you start. That doesn't mean you didn't travel any distance. It just means that you ended where you started, and your change in position is 0. So your change in position can be 0, and also you can cover ground at the same time. So be careful of that. So the integral, which is the sum of all the little tiny changes in S, will give you your change in position, but it will not necessarily give you your distance traveled. You have to analyze it further to understand how that works. Now, what does negative velocity mean? I talked about it briefly in the car example. Negative velocity means that however you're defining positive velocity, with some reference point, you're just moving in the opposite direction. So perhaps in your car, you call going north on a road positive and going south on that same road negative. So a good example of having a 0 displacement would be going to the store and then coming back to your house again. That's 0 displacement because you ended up where you started again. Or if you go down the road and then you do a U and you come back on the road again, that would be 0 displacement because you went in the positive direction and then you turn around and you went in then what's considered the negative direction. So which direction you're going determines whether your velocity is positive or negative. And the area underneath the curve would tell you the displacement in each direction. And the area underneath the curve above the x-axis is a positive displacement. Area underneath the curve is negative displacement. So it's quite possible that your displacement is zero, even though you were continuously moving. So that is a thing that happens. And in fact, you'll recognize this looks like sine or cosine. And sine and cosine are the functions that we often use to model circular motion for that reason. All right, so that tells you a little bit about why the integral is the area underneath the curve.